This video is going to walk you through writing polynomial equations given all of the roots. So not just real roots, but real and imaginary. So back when we had real roots, we always converted the roots into polynomial factored form. So if we had a root at 2, my factor was x minus 2. But now what happens if you have imaginary roots with I in it? Well, what you're going to want to do is multiply it out so that there is no I in your polynomial equation. And then the last thing, similar to what we did in previous videos, was to solve for a if we knew that it went through a certain point. So number 1, it says find the equation of a polynomial with roots at 5, 2i, and negative 2i. So this is telling us that it's a third degree polynomial because we have 3 roots. And now we have to just write them all in factored form. So if I have a root at 5, my factor is x minus 5. Now 2i would be x minus 2i, and then this negative 2i would be x plus 2i. But you have to remember that a polynomial doesn't contain any coefficients with I in it, so we're going to want to multiply this out. And so I'm going to just multiply these two. You can do it using box or FOIL method. And so then this would get me x squared minus 2ix plus 2ix minus 4i squared. Well, I can cancel out these middle terms, and then remember I squared is the same thing as negative 1. So this leaves me with x squared minus 4 times a negative 1, which is plus 4. And you can leave that in factored form, but it no longer has an I in it. So one thing that you're going to see a pattern, if you have imaginary roots that are just like bi, they don't have the a part like this one does down here, 2i and negative 2i, its factor is x squared plus 4. 3i and negative 3i have a factor of x squared plus 9. And 4i and negative 4i have a factor of x squared plus 16. So you're going to start to see a pattern with imaginary roots that are just the bi form. And so if I were to set this equal to 0, I'd subtract 4 and I'd get this x squared equals negative 4, and that's where the imaginary comes into. So you can kind of see a pattern with imaginary roots. But what happens if your roots are of the form a plus bi? So it's this 1 plus 3i. Well, you can't use this nice pattern. So I have a little shortcut for you. So first thing I want to do is write my factor. So I have a root at 2, x minus 2. And you'd think that this is maybe a second degree polynomial, but you have to remember that imaginary roots always come with their imaginary or their complex conjugate. So this is actually a third degree polynomial. So what we need to figure out is what's going to be that next factor. Well, because we have a plus bi and a minus bi, it doesn't factor to something a little bit more prettier, like x squared plus 4. So there's a little bit of a pattern. So you have to think about the 1 is the a and the 3 is the b, okay? And these are going to have factors of the form x squared plus something x plus another number. And so the way to find the number in front of x, it's just negative 2 times a. And then this last number is your a squared plus b squared. And I'm talking about the a and the b from the imaginary number. So to find my other factor, I would plug 1 in here. And so this is going to give me negative 2x. And then the number that goes right here is a squared plus b squared. Well, 1 squared is 1, and 3 squared is 9, and 1 plus 3 is 10. And so then that is our polynomial equation. And then you could box it through to get it into standard form, but that's okay to leave it like this in factored form. And then the last one that we have, this one has a little bit more going on, and it gives us a point that it goes through, meaning we're going to solve for a, our stretch factor. So it says find the equation of a degree 4 polynomial that has a double root at 1 and complex roots at 3i and negative 3i, and it goes through the point 0, 18. So let's start by, there's our a, we're going to have to solve for our stretch factor. It says it's a 4th degree polynomial. If it has a double root at 1, the factor is x minus 1, and then it's squared. And then remember, if we have roots that are just of the bi and negative bi form, I could write it like factors like this, but the shortcut up here is that 3i and negative 3i would be x squared plus 9. So x squared plus 9 is my other factor. So now I got to plug in the 18 for y, and I want to plug in 0 for x and solve for my stretch factor. So then 0 minus 1 is a negative 1, but squared is 1. 0 squared is 0 plus 9 is 9. I'm going to divide by 9, so I get my stretch factor to be 2. So then our final equation is y equals 2x minus 1 squared times x squared plus 9. And you can leave it just like that in factored form. Thank you.